What is going on, everybody? Today in this video, we're going to be doing some civil FE exam review, and we're going to be focusing specifically on mechanics of materials. So I do have a pretty challenging practice problem for you all today. And I think this is going to help you to make sure that you master these concepts for your exam. So without further ado, let's go ahead and get into the video. So before we start, I always like to share what topics that we're covering and how this is going to benefit you for your exam. So as you're studying for your civil FE exam, you're going to be tested on mechanics of materials. And today our practice problem is going to be going through a shear and moment diagrams. So if you have not subscribed to the channel already, make sure you do so as I go through videos and practice problems on all of these concepts that are going to be on your test. And believe me, these subtopics underneath, engineering economics, underneath statics, underneath dynamics, all of these subtopics are really, really important. And so make sure you are subscribed to the channel. Make sure you turn on the bell notifications so that you know exactly when I post. I want to ensure that you pass this exam on your next try. I have free resources and paid resources that will allow you to make your study process a lot easier, as well as an ebook that you all can check out in the links down in the description box below. All right, so enough of me babbling about that. Let's go ahead and get into our practice problem. So this says draw the shear and moment diagrams for the image that we see to the left. As you can see, this is a beam, I would say, and it has a few different loads on it. So I can see here to the left, we have a 6 kilonewton load coming down on the beam. We got a moment happening at kind of this fixed point. We got a reaction of 4.2 kilonewtons. And we have this distributed load along with a roller. And so it already gives us our resultants of our fixed, or if that's a pin, or if it's fixed, whatever it is, and the roller, it gives us our resultants forces for that. So all we have to do is go in and draw our shear and our moment diagram. So as you can see here, I have shown we got shear and I have moment, and we're just going to dig in. So for this particular problem, you shouldn't really need the FE manual. You just use the information that they give you and begin drawing. So for this, we're going to start with a 6 kilonewton force coming down. So I'm going to draw it just like I see it. Try to draw some straight lines for you all today. Yeah. And that 6 kilonewtons stays that way until it gets to this pin, or I'm going to call it a fixed point just to keep things simple. All right, so here, so this is 6. So now it's coming up 4.2 kilonewtons. So I'm going to say here that 6 kilonewtons, and this is a negative 6 kilonewtons, right? Plus 4.2 4.2 kilonewtons is equal to what? So if I do that in my calculator, I get 1.8 kilonewtons. All right. So I'm just going to come up. And this is very rough. Like, it doesn't have to be perfect. Just want a good visual of what's happening at important points on your diagram. All right, so I know that this is going to be 1.8. I feel like I should put negative, but we know it's underneath this line, so say 1.8. And that 1.8 is like that all the way until we get to our distributed load, because there's no other forces, no other shear that's happening along the beam. All right, so once we get to trying to make these lines straight, they don't want to cooperate with me right now, so there we go. All right, so now what's happening? Well, we got a force, a distributed load that's coming down to the roller, 1 kilonewton times like 3 meters. So we got 1 kilonewtons per meter for 3 meters. So I'll go ahead and type that out here. Make it red. So we got minus. So we're at 1.8 right now, right? We're at negative 1.8 kilonewtons. But then we have a minus 1, right? Kilonewton per meter times 3 meters, all right? That's from here to here. Excuse me. Not feeling the best, clearly. So yeah, so we got 1 times 3, right? From the distance of the distributed load to the roller. Then we'll break this up. Then we have a 7.8 kilonewtons coming up, right? And then we have another from the roller to the end, 3 meters times 1 kilonewton per meter. So another 3 times 1. All right, so what does that give us? If you put that in your calculator, what do you all get? You can pause the video, feel free. And negative. Okay, so I get 0, which is fine. All right, but that's just telling me from my distributed load to the end, I get 0, which we should. Started at 0, we should end at 0 for our shear. But what I failed to do is to share pivotal points, because we can't just draw a line that just says from here to here, we're done. All right, that's not the way that goes. So our shear, we have to show it at important points. So from we'll do from the distributed load to the roller, which would be the negative 1.8, right? Because that's where we're starting at. And then it would only be minus 1 times 3. All right, we'll stop it at the roller. And so what does that get us? So negative 1.8 minus 3. That gives us negative 4.8. So I'm going to draw a line down to, looks about right. And we'll call this 4.8. Remember, everything's relative, so I know that 6 is down here, so I don't want to go below 6 in my drawing. All right. Then at this roller is literally going to spike up 7.8. All right. So let's do another. So I know that it went down to negative 4.8, but then we're going to do plus 7.8, which gives us 3. Okay, so I know that at this point it's 3. Okay, and then from there we have 3, and then we'll do minus, right, from the end. So 3 times 1, right? That the rest of that distributed load. Which is equal to 0, which is what we know we got from the long equation, but this is how it should be drawn. Right? And if you're wondering why I'm drawing slants or straight lines up and down, it's basically the slope of your loads. So in this case, the slope just increasingly gets heavier on this distributed load. So it's a constant shear of it's a constant negative shear. So that's why my slopes are coming down. This is going to be really important as we move into moment. So hopefully this made sense. I'm going to shift down to our moment diagram. And our shear diagram lets us know everything we need for our moment diagram. All right, so as we're doing our moment diagram, we are looking at the area. I don't know how I can the area underneath the area within these shapes, all right, in our from our shear diagram. So I tried to do like a hatching, but don't know if that really helped or hurt this image. But basically, we need to find the area that is selected at each point. So I know that we got 6 kilonewtons, all right, coming down a negative 6 kilonewtons. So 6 times, and you need your distance. Moment is force times distance, right? So if we have 6 and then times 3, so that means our moment will be 18 kilonewton meters, right? So I know that negative 18 kilonewton meters dash meters. All right. Okay. So now it looks like we need to look at moment at this fixed point. And that moment looks like it's a positive moment of 36 kilonewton meters. And so I say it's positive because it's going clockwise. So we're going to have a jump up. So I'll just make sure that my work makes sense. So we did 6 times 3 meters. So I did 6 kilonewtons times 3 meters to get my first one, which gave me 18 kilonewton meters. Okay. Now, next thing I'm doing is I'm saying negative 18 plus my 36 kilonewton meters. Kn dash m is equal to 18. You might can't see my work. Dash m. Now you might can see that a little bit better. All right, so now we're gonna make that jump up to 18 kilonewton meters. All right. So I'll put this here, 18. Very nice. All right, so what's happening with moment after that? Well, we go from, we have 1.8 kilonewtons for 7 meters. So the next line item that we'll have will be 18 kilonewton dash meters. And then we'll subtract, because we have, it's a negative area, right? Minus 1.8 times the 7 meters, right? And that's going to bring us to the point of our distributed load. See what we get for that. Seven times 18 minus answer. Okay, so I get 5.4 kilonewton. All right. So basically we're going to slant this. To here. That brings us to our distributed load. Of 0.4. Very nice. Very nice. So then what we're going to look at next is the area from our distributed load to the roller. And so that is going to look a little funny, but we'll take it one step at a time. So I like to break this area up by basically having treating part of it as a rectangle and the other part as a triangle. So hopefully you can see that. That's my rectangle. And then the other part is my triangle. So what is that area? Well, we'll get to it. The first part of it is our 1.8, all right? So it's going to be 1.8, and we'll start by saying that all of this is and actually, I'm sorry. We're going to start with our 5.4 kilonewton meters. And then we're going to subtract, because that's where our area is currently at. But then we're going to subtract the area of this rectangle, which is 1.8. And we're subtracting because it is a negative area. If it was a positive area, we would not be doing that. Okay. So 1.8, and that is kilonewtons. So I won't confuse you there. Times what's our distance? Our distance from this distributed load to the roller is 3 meters. Okay. 3 meters. Okay. And then we're going to subtract again for our triangle. Well, what's the area of a triangle? It's 1/2 times base times height, right? So 1/2 is just 0.5 times the base. We'll call this the base. Well, the base we know is our distance, which again is 3 meters. 3 meters. And what else? 3 meters. Okay. So 1/2 times the base times the height. What's the height? Well, we went from 4.8 to 1.8, right? This is the 1.8, and at the corner of our triangle is the 4.8. So that's a distance or a height of 3 meters. 4.8 minus 1.8 is 3. So. Okay. This should give us, and you probably can't see what I'm trying to show you. So let me drag it over some. So is equal to, that should give us a negative 4.5. And that's kilonewton dash meter. Okay. So Now, how does that get drawn? This is really, really important. So that gets drawn, since this is a negative slope, it's going to be an arc. Let me show you what I mean. So in the reference manual, you have positive bending, then it's going to be concave up. Negative bending, you're going to have concave down. So in this particular case, we have negative bending. So it's going to be concave down. Let's see if I can do this right on the first try. Yeah. Okay. So yeah, this is going to be our negative 4.5 kilonewton dash meter. All right, and then our last one will be let's do green, because we're going to pass this FE exam, right? Let's do some green. Let's do some positive colors. All right, so we're starting out with negative 4.5 kilonewton dash meter. And now we have another triangle, right? And our slope is coming down. This looks like we're going to have some still negative bending. So negative 4.5, and then we're going to add plus, because we have a positive area for our shear. So it's going to be 1/2 times 0.5 base times height. So what's the base? That triangle, oh, it's 3. And what's the height? Is 3. So that should give us 0. And that's a good sign. Should always be getting 0. You want to start with no moment and with no moment. Okay, and we'll draw I did that wrong. So we'll undo that. This again, since it is sloped and it is sloped down, it's going to be concave down. So you can see that this first one was concave down. This one's going to be, again, concave down. All right. So hopefully this made sense. I know this kind of took me a while to explain this shear and moment diagram problem, but hopefully I touched on a lot of the key concepts that you're going to need as you're working with shear and moment diagrams. This was fun for me to kind of play with. In the next video, we're going to be looking at stresses and strains, and really excited about that. If you have not subscribed to the channel already and you've watched this video through its entirety, come on, what are you waiting for? Go ahead, hit that subscribe button. We're literally on the verge of helping 1,000 people pass their civil FE exam. It's going to be huge. And I want to make sure that you have the content and that you are putting in the work and setting aside, time daily as you go to work. Once you get off or before you start work, you're grinding so that you can have this EI behind your name. Really excited for you, and I appreciate you for watching this video, and I will see you in the next one. Peace.